Greetings, amazing algebra learners. Today we're going to continue on with our graphing of absolute values. We're going to learn how to stretch and compress those. But first, what I would love for you to do is get everything that you need, get comfy, and then you're going to use this equation below. I gave you the x values, plug those into the equation, solve for the y, manipulate that standard form into slope-intercept form, and give me the slope and the y-intercept. Pause the video, make sure you have plenty of time to do that. You can check what your slope and the y-intercept is in just a moment, and then we'll move on. Hopefully you got that your slope is positive 3/4 and that the y-intercept is positive 6. If you didn't get those things, make sure you check your signs. Those sign rules always need to apply. Okay, again, we're going to stretch, compress, and reflect absolute values, and we're going to do that by exploring. So you're going to need to set up a lot of tables, and you're going to need to set up where you're going to graph. So if you don't have that already, just take a moment and do so. All right, as you can see, we have 4 different absolute value functions here. And remember, it's a function because it has the f, the parentheses, and the x. And we say that f of x. We remember that that f of x is really just the y value. So that first one, where f of x equals the absolute value of x, I'm going to go ahead and choose a couple of negative values. -2, -1. I always choose 0, always. And then I'm going to do another positive value. So I will do +1. In order to get the f of x, or that y value, we need to plug it into the original parent function. Remember, that's the parent function because nothing is happening to it. I don't have to do anything else except take the absolute value of whatever x is. So the absolute value of -2 is 2. The absolute value of -1 is +1. The absolute value of 0, of course, is 0. And then the absolute value of a +1 is +1. We now have plenty of points that we can go ahead and graph. So I will go ahead and do that. I have 0, 0. I have -1, 1. I have 1, 1. And I have -2, 2. All right. And then I'm going to draw in my lines. It decreases from -infinity to 0, and it increases from 0 to +infinity. Our domain is -infinity to +infinity because x can be any value. Our range, we know that our y's cannot be negative because absolute value is always a positive. So in this case, our range is from 0 to +infinity. Again, this is the parent function. It's the basic graph, the very basic graph of everything that is absolute value. So now let's explore some. In this blue one here, let's go ahead and pick some other values. I'm going to do -3 this time. And I don't know, how about another negative? So -1, and we'll do 0. And let's do +3 this time, just to see what happens. So now again, I'm going to plug it into the absolute value. If I plug it into the absolute value, I have to do that first, and then I would multiply by this negative that's there. So the absolute value of -3 is +3 times that negative that's on that outside. I end up with a -3. That negative on that outside of the absolute value does something specific. Okay, so again, I'm going to take -1. The absolute value of -1 is +1 times that negative on the outside. I end up with a -1. 0, of course, is 0. The absolute value of 3 is 3. It's already positive. Times that negative. All right, so now I have these points that I'm going to graph. 0, 0 is great. Negative 1, negative 1. Interesting. Negative 3, negative 3. All right, and then I have positive 3, negative 3. 1, 2, 3, 1, 2, 3. Sorry, I had to count that out. Okay, I'm going to go ahead and graph this in. Oh, so what ended up happening when I had that negative? What happened when I had that negative? All right, let's continue and do the green. So now I'm going to do the f of x equals 2 times the absolute value of x. Let's throw in some more numbers. I'm going to do negative 1, 0, positive 1, positive 2. Notice I always do negative, and I always do a positive, and I always do a 0. All right, so let's do this. The absolute value of negative 1 is positive 1. Positive 1 times positive 2 is 2. Absolute value of 0 is 0. 0 times 2 is 0. Absolute value of 1 is 1. 1 times 2 is 2. Absolute value of positive 2 times positive 2 is 4. All right, so here we go. I got 0, 0. I have negative 1, positive 2. Positive 1, positive 2. Positive 2, positive 4. Let's see if I counted that right. 1, 2, 3, 4. Good. What if I did negative 2 just because? Would that actually work on the other side? Because you know how we have this one at 4? I wonder if this one's also at 4. So if we did the absolute value of negative 2, that would be positive 2. Oh, it is the same. Interesting. All right, so now I have enough points and I can go ahead and graph. I want you to look at that. What happened to that graph? Look at this green graph in comparison to the purple graph, right? Because that purple graph, that's our parent function. That's as basic as it can go. What changed when we put that positive 2 in front of it? What changed in that shape? All right, so here we go. We got one last one. I have a negative 1/5 x. Whew. This is crazy. Okay, so because I have a you know what? Hang on. Give me a second. I wrote this problem wrong. Give me half a moment. Sorry about that. I had the absolute value symbol in the wrong spot. That was a little weird. Okay. So again, we're going to choose values for x's here. So it's the negative 1/5 times the absolute value of x instead. So let's choose those values again. Let's go ahead and choose the same ones we did for the green. We're going to do negative 1, 0, positive 1, positive 2. I'm going to throw in that negative 2 just because. You know what? I'm not going to do 2s. I'm not even going to do 1s. Love all these kinds of mistakes, right? I just realized this is a fraction. So I'm going to pick numbers where they are divisible by 5 or they're a multiple of 5. So I'm going to do negative 5. I'm going to do 0. I'm going to do positive 5. And I'm going to do positive 10. Because then I know that I'm going to get rid of a fraction. All right. The absolute value of negative 5 is positive 5. Positive 5 times negative 1/5 would be negative 1. If you didn't see that, you can do the math out on the side. 0 is great because the absolute value of 0 is 0, and 0 times anything is 0. So now again, I have this negative 5, or excuse me, I have this positive 5, so absolute value of positive 5 is 5. 5 times that negative 1/5 gives me that negative 1. The absolute value of 10 is 10 times negative 1/5 gives me negative 2. There we go. That looks a little better. If I did negative 10, absolute value of negative 10 is again positive 10, so my result is negative 2. Oof, that took a little bit. Thanks for your patience. All right, so we're going to have that 0, 0. We have negative 5, 1, 2, 3, 4, 5, and negative 1. positive 5. 1, 2, 3, 4, 5, and 1. We have positive 10 and 2. Negative 10 and 2. Wow, that really changed it, didn't it? Draw those lines in. Okay, so for this orange one here, when I had that 1/5, when I had that fraction in front of it, what happened? What happened to the shape? When I had that negative in front of it, what happened to that shape? Take a moment, and on your paper, I want you to write down what you notice about these. What do you notice about the blue, the green, and the orange line in comparison to the purple graph? What's the same? What's different? Well, one thing that I can tell you for sure that's the same is the domain is the same for all of them. The domain is the same for all of them. The x values can be anything. So the x values can be from negative infinity all the way to infinity. And that means no matter where I go on these graphs, if I extend them all the way up, if I extend them all the way down, whatever happens, they're going to eventually get to a value in the x's. That's our domain is always that. Our range varies. Our range varies. Our range varies because of where the direction of our absolute values go. When our absolute values are positive and point up in the positive direction like our parent function, our range then is from 0 to infinity because it's positive. If our absolute value functions point down or are a negative in value, then our range is negative infinity to 0. So it depends on what the shape is, like if it's pointing up or if it's pointing down. That's actually called the reflection. Notice that the vertex for all of this, the vertex for all of these is right there at the origin. So the vertex for everything is 0, 0. That's good to know. The generic equation that works so far for everything that we are talking about is y equals, or f of x equals either plus or minus a number times the absolute value of x. So that a is just any type of number. When it's stretched, that means that it got wider. It got wider. Or I like to say it got fat. It got fat when it was a fraction. So when a was anything less than 0, so it's a fraction. So that generic would be if it was f of x equals plus or minus a fraction times the absolute value of x. Okay, that's that generic. It makes it fat. A fraction makes it fat. Or when a is less than 0. It compresses, or it makes it narrow. It makes it narrow or skinny when a is greater than 0. So it's just a number. It's anything other than that. I call that a number. For me, it's usually like a whole number or something, but it doesn't have to be. It could be an improper fraction, right? But it has to be greater than 0. So in that case, it's f of x is the plus or minus a number, absolute value of x. So those a's change, right? If the a is a fraction, it stretches and it's fat. If a is a whole number, it compresses. The last thing that you need to realize is that if it reflects, it's negative. If it reflects, there's a negative. So when it reflects, it either reflects over the x-axis and makes it go down. So that's when it's negative. So this is when f of x is negative a.